Hello, myself Dr. Anush Purwar. Today I am taking lecture on storage and distribution reservoir. As a measure of safety against the interruption of the supply from accident to conduit or machinery, distribution are of great value. It gives cheaply additional safety against interruption when units may require duplication. With respect to quality, these reservoirs are of great advantage as they provide an additional opportunity for sedimentation and making it possible to avoid taking water from streams during periods of great turbidity. Working of balancing or distribution reservoir. When the for water exceeds the rate of supply, the water flows into the distribution system both from the elevated distribution reservoir as well as water through direct pumping by means of a bypass loop as shown in the figure. By closing valve at A but keeps valves B, C and D open. When demand for water is less than the rate of supply, the required demand is met by water pumped through the bypass loop, while the balance pump water fill up the balancing reservoir by closing the valve D but keeping valves A, B and C open to regulate the flow. Functions of the distribution reservoir. They absorb the hourly variation in demand and allow the water treatment units and pumps to operate at a constant rate. This reduces the running, maintenance, and operational cost and improves of efficiency. Here, running, maintenance, and operation in short form we can write RMO. They help in maintaining constant pressure in the distribution mains. In their absence, the pressure falls down as the demand of water increases. The pumping of water in shift is made possible by them without affecting the supply. Thus, 8 to 12 hours of pumping can be carried out so as to supply the whole day demand. The water stored in these reservoirs can be supplied during emergencies such as breakdown of pumps, heavy fire demand, etc. They provide an overall economy by reducing the sizes of pumps, pipelines, and treatment units, and this is the most important aspects of service or distribution reservoirs. Types of distribution reservoirs. Surface reservoirs. A surface reservoir may be constructed at ground level or below the ground level. Hence, they are also known as ground reservoirs. They are generally constructed at higher points of the area to be served. If the area to be served is undulating, having more than one high point, more than one distribution reservoir may be provided in that case. In a gravitation type of distribution system, water is stored in the ground distribution reservoir and then directly sent from there to distribution main, which are situated at lower elevation. In a combined gravity and pumping system, the treated water is first stored in a ground reservoir and then pumped to an elevated surface reservoir from which water is supplied into the distribution mains. Elevated reservoirs. Elevated reservoirs are mostly rectangular or circular overhead tanks erected at a suitable elevation above the ground level and supported on the towers. They are constructed where the pressure requirements require considerable elevation above the ground surface to serve multi-storied building. They are provided in the area where the combined gravity and pumping system for water distribution is adopted. Water is pumped into these elevated tanks from filter units and then supplied to the consumer. Standpipes. Standpipes are a kind of elevated tanks without any supporting towers for resting the tank body. They are tall cylindrical cell resting directly on the ground. Standpipes are generally 15 to 20-meter high and 10 to 15 meter in the diameter, as seeing pipes in the right picture. Types with respect to construction material. With respect to form of construction materials or the construction materials, reservoirs may be classified as earthen, masonry, reinforced concrete, or steel. Position and elevation of reservoirs. If the service storage is to be of maximum value as a safeguard to the undertaking against breakdown, then it should be positioned as near as possible to the area of demand. From the service storage, the distribution system should spread directly with such a ramification of mains that no single breakage could cause a severe interruption to the continuity of the supply. There should be sufficient interconnection between the distribution mains so that if a breakdown of any one mains occurs, the supply may be maintained by rerouting the water. It is not always possible to have a high point which is in the center of the distribution area, and in such circumstances, the best possible should be done. If the high point is remote from the area of demand, the area is kept to feed the demand by to measure means from the service reservoir. If there is some high ground which is not quite high enough, then a water tower or several water towers may be provided to meet the requirement. It has to be seen that service reservoir is located at such an elevation that a steady pressure is available at all points of the distribution system. If the distribution area varies widely in elevation, it may be necessary to use two or more service reservoirs at different levels so that the lower areas do not receive an unduly high pressure. Generally, 45 meter to 75-meter static pressure is that which suits best to the domestic distribution system. Pressure below 95 meter may cause trouble in supplying extensive distribution areas, and pressure above 120 meter may be too high to result in excessive leakage losses. In a pumping system, the pumps are generally located near one side of the city, and for the best result, the reservoir should be located at some point on the opposite side of the distributing system. Design for storage. Mass curve method. A mass diagram is the plot of accumulated supply or demand versus time. The supply is also known as inflow and demand is as the known as the outflow. First mass curve of supply known as the supply line is drawn, and over this demand curve is superimposed. The amount of balancing storage is determined by adding the maximum ordinate between the demand and supply lines. First hourly demand for all 24 hours from the day of maximum requirement is determined. Cumulative demand is plotted against time, which is known as the mass curve of the demand. Next, cumulative supply against time is plotted, which is a straight line if the supply is constant. The storage required is calculated as the sum of the two maximum ordinates between demand and supply lines. So here the example, a town has population of 1 lakh. It is to be supplied with water at the rate of 200 liters per head per day. The variation in demand is as follows. 6 a.m. to 9 a.m. this is 40% of the total. 9 a.m. to 12 noon 10%. 12 noon to 3 p.m. 10%. 3 p.m. to 6 p.m. 15% of the total. 6 p.m. to 9 p.m. 25% of the total. Determine the capacity of the service reservoir when the pumping is at a uniform rate from 6 a.m. to the 6 p.m. So solution, total daily requirement population 1 lakh into 200. So total daily requirement is 200 milliliter. So calculation 6 to 9 a.m. number of hours 3. So rate of demand 40% of the 20 ml. So demand in ml 8. So cumulative demand in milliliter 8. In that case 40%. As similar way 9 to 12 noon this is the 10% of the 20 ml, so demand is ml2. So cumulative demand in column in row 2 this is 10. In similar way we calculate the 12 noon to 3 p.m, 3 p.m to 6 p.m and 6 p.m to the 9 p.m. So demand and supply lines have been drawn in firm and dotted lines respectively in figure. So demand is firm and the supply line is the dotted line. Two maximum ordinates enclosed between demand and supply lines have been read out as 5 million liters and 3 million liters respectively. So this is the figure. Here the supply lines and the demand curve is against the time. This is the continuous line and we calculate the maximum ordinate as we shown in the figure. This is the 5 ml and the 3 ml. So total storage required the 5 plus 3 is equal to 8 million liter. Now analytical method. In this method, cumulative hourly demand and cumulative hourly supply are tabulated for all the 24 hours. The hourly excess demand and hourly excess supply are worked out. The summation of the maximum of the excessive of demand and the maximum of excessive of the supply gives the required storage capacity. So here the example, calculate the storage required to supply the demand shown in the following table if the inflow of water, inflow means supply, to the reservoir is maintained at a uniform rate throughout the 24 hours. So here the time 0 to 4, demand is milliliter 0.48, 4 to 8 0.87, 8 to 12 1.33, 12 to 16 1, 16 to 20 0.82 and 20 to 24 0.54. So here the solution, total demand during the day 0.48 plus 0.87 1.33 plus 1 plus 0.82 plus 0.54. This is equal to the 5.04 million liter. So total supply during the day is equal to total demand is equal to 5.04 million liter. Because here is a constant hourly supply, so hourly supply is equal to 5.04 divided by 24 is equal to 0.21 milliliter. So 4 hourly supply 0.21 into 4 is equal to 0.84 million liter. So this is the all the data in this table. As in first column this is the time in hours, in second column demand in million liter as given, cumulative demand calculated in column 3, pumping in milliliter this is the constant, put the in column 4, cumulative pumping in column 5 and then calculate the excess of the demand. This is the column 3 minus column 5. So these positive values put the here only. So here the for the time hours 8 to 12 and 4 to 6 12 to 16 and 16 20. The value put here comes after column 3 minus column 5. So value comes 0.16 and 0.32 and 0.10. And next column put the axis of the supply, column 5 minus column 3. Here again we put the only the positive value. So in that case, first row 0.36 and second row again the 0.36. So from our the table, it is observed that the maximum of the excess of demand is equal to 0.32 million liter, and the maximum of the excess of supply is equal to 0.6 million liter. So total storage required 0.32 plus 0.36 is equal to 0.68 million liter, is equal to 6,80,000 liter. Here is another example. An overhead tank is to be provided for a town water supply. Given the following data, calculate the minimum capacity of the tank without any fire demand. So tank is empty between, it is given 12 to 15 hours. Average water supply is 16,666 liter per hour. Rate of pumping is 25,000 liter per hour, and hour of pumping is a 4 to 12 and 15 to 23, because tank is empty at the time of the 12 to 15 hour. So this is the table. Here the given time duration, then total hours and drawn off factors, then water pumps, and then water consumed. So solution as given in the question, the tank is the empty between 12 and 15 hours. Hence we shall start from the serial number 5. At serial number 6, storage is positive 16,666. Again, at serial number 7, it has reduced by 6,666 liter. Hence, net storage is 10,000. Means 16,666 minus 6,666. So answer comes 10,000. And so then proceed the serial number 8, 9, then 1, 2, 3, and finally at the 4. So here the table in first serial number, second times, and then time duration, and then total hours in that time duration, then water pumps, then water consumed, then accumulated. This is the draft. This is column 4 minus column 5. So value, some value comes in the negative and some value come in the positive. So and the water in service reservoir in liter, then this is in the column 7. So now from column 7, it is clear that the maximum balance storage is 35,000 liter. Hence the minimum capacity of the tank should be that now 35,000 liter. This is the answer. Now another example, a service water tank is receiving water from the treatment plant at a rate of 200 meter cube per hour for 24 hours. The high lift pump are lifting water from the same tank at following rate: 4 to 14 hours at the rate of 120 meter cube per hour, and 15 to 24 hours, this is the at the rate of the 400 meter cube per hour. Determine the capacity for the reservoir service water tank. So here the solution. The problem has been solved as given in the table. The cumulative supply over demand is 1800 meter cube. Hence the capacity of the tank should be the 1800 meter cube. So we are seeing the we prepared the following table for that solution. In column 1, time in hour, demand from the clear water tank lifted by the high lift pump. This is in table 2, because 0 to 4 there is nil demand, and for the 14 to 15 hours there is again the nil demand, and 4 to 14 demand is total demand is 1200 meter cube, and 15 to 24 this is the 3600 meter cube. And cumulative demand for clear tank, in first case nil 0, for the second this is the 1200, again this is the 1200, then finally this is the 4800. So supply in the clear water tank for the first 4 hours, this is 200 into 4 is equal to 800. For 4 to 14 this is the 10 hour total, so here the 2000, and then this is the 1 hour only, so here 200, and next this is the 9 hours, so total 200 into 9 is equal to 18 hours. Then cumulative supply 800, 800 plus 2000, 2800, 2800 plus 200, 3000, and 3000 plus 1800 is equal to 4800. So cumulative draft is equal to column 5 minus column 3. So value comes the in first column 800, second column second first row is 800, second row is 1600, and third row is 1800. So total capacity of the tanks will be the 1800 meter cube. Here the another example. For a town, daily requirement of water for supply to the population is 2 lakh liters. The pattern of the draft is as 6 a.m. to 9 a.m. 30% of the day supply, 9 a.m. to 4 p.m. 35% of the day supply, 4 p.m. to 7 p.m. 25%, 7 p.m. to 6 a.m. 10%. The pumping is done for 10 hours a day from 8 a.m. to the 6 a.m. Find out the storage capacity of the distribution reservoir for the water supply scheme. So here the solution: total daily requirement 2 lakh liters. Now the cumulative demand covered is tablet as it in table. So first column period, second rate of demand as given in question. Here the total demand is the 2 lakh liter. Demand is liter. Then comes 60,000. First row, second row 70,000, third row 50,000, and fourth row 20,000. So cumulative demand, first row 60,000, second 1,30,000, third 1,80,000, and then 2 lakh. So mass curve of the demand has been plotted as shown in the figure. Supply versus time and demand versus time. So here is the maximum ordinance for A is equal to 30,000 liters, and for B this is the maximum ordinance 42,000 liters. So total demand is met for the 10 hours. So rate of supply is 2 lakh divided by 10 is equal to 20,000 liter per hour. So two maximum ordinates comes: A is equal to 30,000 liter and B comes the 12,000 and 42,000 liter. So total storage capacity should be the A plus B is equal to 72,000 per liter. So here is all about the distribution. Thank you.